Good morning, all of you. Welcome to Sri Jayendra rank zone. Now we are in group 14 elements. In this lecture, we are going to learn more about group 14 elements. So please listen carefully, all of you. Let us start group 14 elements. Second lecture, group 14. And in P block, fifth lecture. Let us start now. Allotropes and compounds of carbon now. So in this lecture, we are going to learn about allotropes and compounds of carbon. Due to small size, high ionization enthalpy, high electronegativity, and unavailability of d orbitals, carbon exhibits anomalous behavior. So in this group, carbon is exception compared to all other elements because of its small size, high ionization enthalpy, high electronegativity, and unavailability of d orbitals. Carbon exhibits anomalous behavior. Its maximum covalence is limited to 4. It can form p-pi bonds, multiple bonds with itself and other atoms of small size and high electronegativity. So examples are in carbon C double bond C. This is called C double bond C. It is forming p-pi bonds, and C double bond O, p-pi, and so on. So up to cyanide. So now in this lecture, what is allotropy? Allotropy means the existence of an element in more than one physical form is called allotrope, and the property is called as allotropy. The existence of an element in more than one physical form. Here I write the existence of an element the existence of an element in more than one physical form is called allotrope. More than one physical form means it can be crystalline amorphous, that's why it is called allotrope. Physical form is called allotrope and the property is called as allotropy. So carbon exhibits allotropy. Let us see now. So why carbon is exhibiting allotropes, and it is anomalous to other elements because of its small size, high ionization enthalpy, high electronegativity, and unavailability of d orbitals. These are the four reasons: small size, high ionization enthalpy, high electronegativity, and unavailability of d orbitals in carbon. Carbon atoms have the tendency to form covalent bonds among themselves to form chains and rings, and this phenomenon is called as catenation. The catenation tendency decreases from carbon to tin. Lead does not show catenation, except that remaining elements exhibit allotropy. So what is allotropy? Just now we have discussed the existence of an element in more than one physical form is called allotrope, and the property is called as allotropy. So except lead, all other exhibits, all other elements, that is carbon, silicon, germanium, and tin, exhibits allotropy. Continuation now. Carbon exhibits many allotropic forms, that is crystalline allotropy and amorphous allotropy. So it consisting of mainly two allotropes, crystalline allotropy and amorphous allotropy. So in crystalline allotropes, it is diamond and graphite. Diamond and graphite. Crystalline allotrope is diamond and graphite. And amorphous allotrope is coal, charcoal, coke, etc. So many allotropes are there for carbon. So all these are nothing but carbons only. Coming to allotropes. So coal, coke, charcoal, anthracite, etc. These are called amorphous allotropes of carbon. These are called what? Amorphous allotropes of carbon. That is coal, coke, charcoal, anthracite, etc. Purest form is anthracite. Softest form is lamp black. Lamp black is also a carbon black. It is used in the manufacture of tires. So lamp black is nothing but what? It is also called as carbon black. It is used in the manufacture of tires. Manufacture of tires, which are used for vehicles. And purest form of carbon is anthracite. This also they'll ask in examination. What is the purest form of amorphous form of carbon? It is anthracite. Anthracite is the purest amorphous form of carbon. Please note it down. Continuation. Crystalline isotopes we have diamond, graphite, and fullerenes. Diamond, graphite, and fullerenes are the crystalline allotropes of carbon. So let us see now diamond. It is crystalline form of allotrope. It is has rigid three-dimensional network of carbon atoms, which makes it very hard. The hardest substance, natural substance, is diamond only. Diamond is nothing but hardest natural substance. Natural means it is found by itself. So that's why it is called hardest natural substance in the elemental form is nothing but diamond. Diamond is the hardest natural substance. The CC bond length in diamond is 154 picometers. These are all the statement based questions they ask. Which are the following statements is correct regarding diamond? Which are the following statement is incorrect regarding diamond? So the CC bond length in diamond is 154 picometers, and in diamond each carbon atom undergoes sp3 hybridization and forms four bonds with four other carbon atoms tetrahedrally. So as it is undergoing sp3 hybridization, its shape is tetrahedral. Thus, diamond is the hardest substance. Therefore, it is used as an abrasive for sharpening hard tools, for cutting of tools. You can say sharpening hard tools are nothing but for cutting of tools. We can use diamond. So all the major important points from diamond is covered. This is the structure of diamond. So the bond length is diamond is CC bond length is 154 picometer. This is called what? CC bond length. C single bond C bond length is 154 picometers. So diamond is the hardest substance known, and it occurs in nature in the free state. Hardest natural substance. It occurs as octahedral crystals. Insoluble. Diamond is insoluble in all solvents. Diamond is insoluble in all the solvents. So it is not at all soluble at all. It burns in air at 90 degrees to give carbon dioxide. It burns in air. It burns in air at a temperature of 900 degrees, a very high temperature, to give. So it means diamond here, to give carbon dioxide. So diamond is insoluble. This is insoluble in all the solvents. It burns in air to at 90 degrees to give carbon dioxide. So some more properties of diamond, let us see now. So before that, I would like to add some more points about diamond. So because it is not given all points properly. Next, very important point is diamond is a bad conductor of heat and electricity. Diamond is a bad conductor of diamond is a bad conductor of heat and electricity. Diamond is a bad conductor of heat and electricity. So it is very, very important point. And it is having high refractive index. Diamond has high refractive index, due to which it has high refractive index, and its value is almost 2.45 highest. Sorry, 2.45. Refractive index value is 2.45, due to which it is very shiny, and it is a bad conductor of heat and electricity. Diamond is a bad conductor of heat and electricity. So these are the main points about diamond. It's related, it has high relative density, even density also is very high density, due to which its density is almost equal to 3.5. So it has high density. All these points you note down in your classwork. Since all the four valence electrons on each carbon atom are used up in making four covalent bonds with other carbon atom, therefore the average value of CC bond order in diamond is 1. So CC bond order is 1. CC bond length is 154 picometers and CC bond order is equal to 1. These are the main points about diamond. It is insoluble in all solvents. At very high temperature, 90 degrees C, diamond burns in air to form carbon dioxide. And these are the main points about diamond. And diamond reacts with fluorine at 700 degrees C to form CF4. Diamond combines with fluorine, combines with the flowing at 700 degrees C to form carbon tetrafluoride. To form carbon tetrafluoride. These are the main points about diamond. So please make a note of it. And what are the use of diamond? It is used for making glass cutter and as an abrasive, and for making and polishing hard materials, and also for making precious gems and jewelry. So diamond are used in jewelry also. As we already know, it is very costly. Next continuation. Now let us see graphite. It is also a crystalline allotrope of carbon. It has, this is also very important, graphite and diamond, definitely they'll ask a question based on this. It has a layered structure. Layers of carbon atoms are held by weak van der Waals forces, and distance between them is 340 picometers. One layer to another. Layer distance. This is called what? Layer distance, 340 picometers. In graphite, each carbon atom is undergoing sp2 hybridized. You can make a note of this. It is undergoing sp2 hybridization and form three bonds with three other carbon atoms to form hexagonal rings. The CC bond length is 142 picometers. One free electron presented on each carbon gets d because it is only three carbon atoms. So definitely it has one free electron on each carbon gets delocalized and forms pi electron core. Due to this free electron, graphite acts as a good conductor of electricity. Very, very important point. So due to this free electron only, graphite acts as good conductor of electricity. So these are the main points about graphite. Continuation. Due to this free electron, graphite acts as good conductor of electricity. Graphite acts as a good conductor of heat and electricity. And due to weak van der Waals forces in graphite, layers can slide one over the other, slippery nature. Layers can slide one over the other, making it soft and slippery. For this reason, graphite is used also as a lubricant for engine oils. Very, very important. Silicon carbide, an intermediate in the manufacture of graphite by extrusion process, is used as abrasive as it is hard substance. So these are the main points about graphite. So this is the structure of graphite, hexagonal rings. This is called hexagonal rings, and layer to layer. This is first layer, second layer, and third layer. They form slippery in nature. Due to this layer-like structure, they form slippery and soft also, soft and slippery in nature because this layer slides one on another, and the distance between one layer to another layer is 340 picometers, and the bond length between CC bond length is 142 picometers or 141.5 picometers. So these are the main points regarding graphite. So in graphite, carbon undergoes what type of hybridization? sp2 hybridized. CC bond length is 141.5 picometers. The average CC bond order in graphite is 1.33. So CC bond order, average CC bond order in graphite is 1.33. Since each carbon atom in graphite is sp2 hybridized, so bond order is called double bond plus two sigma single bond by number of atoms attached to each other. So it will get is equal to 1.33. Graphite burns in air at 700 to 800 degrees C to give carbon dioxide. So graphite that is carbon in the form of graphite burns in air at 700 degrees C, very high temperature, to form carbon dioxide. To form what? Carbon dioxide. So graphite and diamond are interchangeable. Graphite at 1600 degrees C, 1600 degrees C, and very high pressure, that is 50,000 to 60,000 atmospheres. 50,000 to 60,000. Normally, it is not possible. 60,000 atmospheres, it can be changed into diamond. So graphite can be changed into diamond at very, very high temperature, that is at 1600 degrees C, and very, very high pressure, that is 50,000 to 60,000 atmospheres. When graphite is heated with vapors of potassium, rubidium, cesium at 300 degrees C, it forms C8M. That is, graphite is diametic and C8M is parametric. So graphite combines with metals directly. It forms C8M, where M is equal to potassium, rubidium, cesium, and francium. Potassium, rubidium, cesium. So when graphite is heated to 300 degrees C, vapors with vapors of potassium, rubidium, cesium. So it forms CATM. What is this CATM? It is paramagnetic in nature. Generally, graphite is diamagnetic and this CATM molecule is paramagnetic in nature. What is M? M can be potassium, rubidium, cesium. Paramagnetic in nature. All these are the important points based on graphite. So graphite is thermodynamically more stable than diamond. Very important. Graphite is more stable than diamond. Graphite is more stable than diamond thermodynamically, means with the respect to heat, because the heat of formation of the Gibbs free energy of graphite is 1.9 kilojoules per mole. So graphite is more stable than diamond thermodynamically. So these are all the important points based on graphite. So what is graphite? You understood clearly. So this is, it has layer-like structure and the layer distance is 340 picometers and CC bond length in graphite is 141.5 picometers and hybrid CC hybridization is sp2, a carbon undergoes sp2 hybridization in graphite. Average CC bond order in graphite is 1.33, slightly higher than diamond. It is equal to 1 bond order, and graphite on heating at a temperature when burns in air at a temperature of 700 degrees C, it forms carbon dioxide, and graphite can be converted into diamond provided the temperature is very high, that is 69 degrees C, and pressure is also very high, that is 50,000 to 60,000 atmospheres. So these are the main points related to graphite. Definitely they'll ask statement based question regarding diamond and graphite. Next we have next allotrope is fullerenes. It contains 26 membered rings. How many rings? 26 membered rings and 12 5-membered rings. So 12 5 is 60, 26 is 120. So a 6-membered ring is fused with 6 or 5-membered rings, but a 5-membered ring can only fuse with 6-membered rings. The entire carbon atom is equal and they undergo hybridization. They undergo what? Hybridization. Each carbon atom forms 3 sigma bonds with the other 3 carbon atoms. So the remaining electron at each carbon is delocalized in molecular orbitals, which in turn give aromatic character to molecule. What character? Aromatic, that is like benzene. So fullerenes. Fullerenes are also very, very important. From these carbon allotropes, definitely they'll ask you statement-based question. So graphite and fullerenes, to some extent they are same. There are 12 5-membered rings and there are 26 membered rings. 6-membered rings are fused to other 6-membered rings as well as 5-membered rings. 5-membered rings are fused only to a 6-membered rings only. These are both single and double bonds. They are both single and double bonds. Continuation. This ball-shaped molecule has 60 vertices. How many vertices? It has 60 vertices and each one is occupied by one carbon atom and it also contains both single and double bonds with CC bond distances of 143.5 picometers and 183.5 picometers. For single bond, it is 143.5 and for double bond, it is 138.3 picometers respectively. Spherical fullerenes are also called as buckyballs in short, or we can say it is just like football. Almost resembles like football. So these points are very important. All these points you have to note down in your classwork. Then only you can answer statement-based question. So this is called fullerenes. 60 carbon atoms. Minimum it should be 60 to 120. So all this dotted, black color dotted ones, they are nothing but carbon atoms. So this is called buckyball of fullerenes. So it contains near about 60 carbon atoms. So structure of Buckminster fullerene. The 60 carbon atom is called as Buckminster fullerene. Buckminster. The name of this compound is this carbon is Buckminster fullerene, and it is nothing but comprising of C60. C60, 60 atoms of carbon will be 60 atoms of carbon is present in this. And carbon atoms in fullerenes is again sp2 hybridized. Carbon atoms in fullerenes. Carbon atoms are undergoing sp2 hybridized. Please make a note of this point. So they undergo sp2 hybridization. Carbon atoms are sp2 hybridized. The followings being covalent are soluble in organic solvent. These followings are soluble in organic solvents such as benzene, ether, etc. Organic solvents such as benzene, C6H6, ether, etc. Next point, followings can be reduced electrochemically and react with elements of group 1 to form solids such as K3C60. It forms a compound with first group metals, that is K3C60. This compound behaves as superconductor. This is called superconductor below 18 degrees C. Superconductor below 18 kelvins, which implies that it carries electric current with zero resistance. Superconductor means what? It carries electric current with zero resistance. Zero resistance. Very, very important point. Please make a note of this, children. So K3C60, it forms. When does it forms K3C60? Followings can be reduced electrochemically and react with elements of group 1 to form solids such as K3C60. This compound behaves as a superconductor below 18 kelvins. Below 18 kelvins, it behaves like superconductor. What is superconductor meaning? It carries electric current with zero resistance. It carries electric current with zero resistance. So these are the important points of followings. And what are the use of followings? They find applications in nanotechnology. Followings have applications in nanotechnology. Now we are going to do this on nanotechnology. Nowadays it is becoming popular. So these followings are used in nanotechnology. Followings are used in nanotechnology. It has no practical use. Do not have any practical use. It is used in nanotechnology. Followings are used in nanotechnology. Very, very important point. Please make a note of this. The structure of C60 Buckminster following, not that molecule has the shape of soccer ball like football. It is very important to know that graphite is thermodynamically more stable allotrope of carbon, and therefore the heat of formation of graphite is taken as zero. And delta H value of heat of formation values of diamond and following are taken as 1.90 and 38.1 kilojoules per mole respectively. As I told you, it is very important to note that graphite is thermodynamically allotrope more stable allotrope. So with this, I'm